Latin square design. On the surface, this one just sticks out compared to the rest, as it doesn't have any weird statistical phrasing or anything. It's just Latin square designs, or it could be roughly translated to 4 equal-sided arrangement with ties to the language of Rome. It seemed simple, and looking into it, it has a lot of practical applications. We see it in mathematical puzzles, board games, mathematics, the popular game Sudoku. We also see it in agronomic research, methods in behavioral pharmacology, facets of dyslexia and its remediation. Okay, maybe it's not so simple as I thought, but what is a Latin square design? Well, according to businessdictionary.com, a Latin square design is an experiment design that can be used to control the random variation of 2 factors. We can visualize what this actually looks like on a graph. It's very similar to a simple comparison, however where it differs is in its variables. A normal comparison will typically test 2 different variables, but the Latin square design tests 3, 2 on the main axis and 1 for all the other data values. In the end, the amount of results ends up being n squared, where n is the size of the dataset on one axis. For example, if we wanted to measure the effects of a medicinal drug, a normal comparison would test the type of drug and its final effect. However, using Latin square designs, we can add time as a variable and see the effects over time it has on the patient. This adds another dimension to the matrix and adds more possibilities to what we can learn about the group of data. How the Latin square design manages to work is that no variable is repeated twice. Say we have the test subjects A, B, and C. These subjects are lined up on a 3x3 Latin square. Each row will have one of the subjects, and each column will also have one of the subjects. If done correctly, there will be an even array of values with none repeating and none missing one of the subjects. It's useful to use a Latin square because you can eliminate possible outliers just with the nature of the Latin square. Just by observing the data and using it, you can see possible outliers or large extraneous values by scanning over the matrix that is formed. However, one of the problems using a Latin square is in the name itself. It's a square, so the amount of values that you test on each side must be the exact same for the Latin square to function correctly. Let me demonstrate the Latin square design with an example. An engineer wants to test out different steel alloy compounds to use for train rails for different trains to run across at different points. The different compounds are represented by C1, C2, C3. The different trains are represented on the y-axis by train 1, train 2, and train 3, and the different runs that they perform are represented on the x-axis. From the results gathered, we can see a trend. Train 2 seems to damage the rail compounds more overall, while the first compound seems to hold up the best on average. Because of these results, and the use of the Latin square, we can suppose that the first compound would be the most effective in maintaining its integrity when tested against the stress of a train.